You click on
present.
that button now.
Yeah, your entire screen.
There your entire
Okay.
screen is there or window is there. You can keep your PPT open and share your entire screen, or else you can choose the window and from there you can pick up your PowerPoint presentation files.
Okay.
You put it your entire screen.
Present now window.
From there you can.
Wait a minute, I think it's open. I need to open it. Okay, now. Window. Oh, yeah, there. Got it?
It is coming, sir. It has come, sir.
Yeah. Okay. I'm ready whenever you want. Okay.
Okay, sir. We will wait for 5 more minutes.
Sure. No problem. I'm here.
Okay, sir. Thank you, sir. I'll start the program, sir. Participants
Yeah, sure.
will slowly join. So we have participants around 75 plus, sir. By the time
Okay, good.
most of them will be here. So good evening to
Sure.
all the all the participants, and welcome you all to the 10th lecture of the faculty development program on shallow and deep foundations. So we are fortunate to have with us Professor M.R. Madhav sir, who is a renowned geotechnical expert, not only in India, worldwide. Right. So most of you might have listened to him on many occasions. So I am very happy that sir has accepted my request to deliver lectures in this FDP. Though you are aware of Professor M.R. Madhav sir's achievement, as a formality, very briefly, I'll introduce Professor Madhav to you. So Professor M.R. Madhav is Institute Fellow of IIT Kanpur, and he is AICTE INAA Distinguished Visiting Professor. Presently serving as Visiting Professor at IIT Hyderabad and as Professor Emeritus at JNTU Hyderabad. He is serving as resource person for RGUKT, and he has been serving as advisor or consultant to several organizations, various state and central government organizations, and other local bodies and consulting organizations. He is well known internationally as researcher, teacher, and consultant. He has contributed significantly to the practice of geotechnical engineering over the last 5 decades. He has worked at several universities abroad, including Australia, Canada, Japan, Belgium, UK, etc. Professor Madhav's research interests span the whole gamut of geotechnical engineering. He has guided more than 45 doctoral and several master's theses. He has co-authored books entitled Lowlands Development and Management, Foundations and Soft Ground Engineering, Challenges on Mekong Delta. He has authored more than 500 publications in referred international and national journals and conferences. Professor Madhav is fellow of Indian National Academy of Engineering, Indian Geotechnical Society, and Institution of Engineers India. He served as president of International Association of Lowland Technology during the period 2010 to 2018, and he has served as vice president for Asia of International Society for Soil Mechanics and Geotechnical Engineering during the period 2005 to 2009. He is recipient of Programe Award. He has also received Professor Mehra Research Award, Pandit Jawaharlal Nehru Birth Centenary Research Award, and he has also received Doctor of Science from Indian Institute of Science. He received Distinction in Engineering and Technology from Central Board of Irrigation Power, and he is also recipient of Bharat Ratna Mokshagunda Vishweshwaraya Award from Institution of Engineers India, AP State Center, and he has received Gopal Ranjan Research Award of IIT Roorkee, and several awards are there. To mention some more awards, IGS MS Jain Award, Vishwakarma Award for Academic Excellence from Construction Industry Development Council, Dinesh Mohan Award from IGS, and also received a Distinguished Teacher Award from IIT Kanpur, and a Distinguished Alumnus Award from ISC Bangalore. So he has been serving as a reviewer for many international journals and received the Outstanding Reviewer Awards from ASC Journal and other reputed international journals. So with this introduction, I invite Professor M.R. Madhav sir to deliver his lecture on the topic of load tests on piles. Please, sir.
Thank you, Professor Reddy. A very nice afternoon to Professor Reddy and all the participants. I'm delighted and very pleased to share with you some of my thoughts and concerns or procedures for the pilot test. But first, let me congratulate Professor Reddy. I'm amazed at his energy after conducting IGC 2020 last month online, which is for the first time. I'm also surprised that he's able to organize this FDP lasting almost 2 weeks and coordinating with several teachers or people who are going to give lecture. Hats off to Professor Reddy, and I would also like to thank him for giving me this opportunity. So today, I would like to share with you some information and details with regard to pile load tests. People may think it's just routine load tests as the construction industry or the contractors think, just do one test and get away with it. But I found that it's one of the most powerful ones in terms of what we can learn from one pile load test. So in my presentation today, I would like to cover the following topics. What are the kind of types of tests we have? What are the procedures? The more important thing is interpretation. Following that, you can diagnose what's happening in terms of the response of the pile from the load settlement data or whatever you get from there. Then we can analyze the same and get back some of the ground interaction parameters too. So there is a variety of things you can get, and don't think that pile load test is simple just to confirm allowable pile load, which I think is one of the necessary things, but it's not fully complete in that respect. So we'll try to cover many of these aspects as much as we can, and I would like you to share anything in case you want to. At the end of presentation, send a note or message, we can reply to that. The kind of tests we do on a vertical pile are axial compression, which is the most common one, wherein you would like to know what is the maximum load it can take and what will be the allowable settlement at the usual working load condition. Then, of course, you do the design. Basically, why we need the test is because when you design a pile, for example, even 0.6 meter there, 12 to 13 or 14 meters long, it goes through several soil strata. And we hardly know any information. Maybe we'll have some SPTN values. If you are very good, you can probably have static cone QC. And some people try to get the so-called undisturbed sample. And we know in India, our sampling is not all that perfect. And so we end up getting some very, very unrepresentative values. So based on that, we try to design saying that the allowable load for the pile is 90 tons or 900 kPa or 800 kPa. For us to accept the design, you need to verify. And that is why we go through this axial compression test. Similarly, when we have a building or a tower, instead of compression, you may have a pull-out, which means because of either wind load or lateral loads or whatever may be the reason, could be uneven ones, the pile can be subjected to an uplift or a upward force. We call it pull-out load. The third one is it's also the buildings or structures could be subjected to, let's say, wind load, which gives you lateral forces. Same thing with seismic forces, or for that matter, if you have an eccentric load, etc. In case of bridges, you could have lateral load from the water load, the traffic, whatever you have. So you need to find out the capacity of the pile under lateral conditions too. But today probably we'll concentrate more on the compression side, but we'll also cover the rest of them as and when it turns out to be. So when we do the axial compression test, we have two stages. Before you start the project, you would like to verify whether the design is correct or not. So let's say you designed the pile for 80 tons safe load. The code and also your own requirement would be that let's try to do an initial load test before the whole project is taken so that you can verify your design. So what we do is we do initial load test where the applied load could be at least 2.5 times, preferably to failure. The reason is you have to make sure that our design is valid. There are situations where we found that our design is either overly conservative. We gave it allowable design load of 80, but in practice we got 120. There are situations where the initial design was non-conservative. The actual allowable load realized was less than 80 tons. So which means now we can revise the design based on actual experience at the site. As I said, ground is one parameter, one quantity entity whose properties can never be ensured. If even a top consultant, somebody says, I know everything, don't believe him. Maybe God knows, but we don't know whether God even knows or not. So basically, I have very little faith in this pure theoretical one unless it is validated. So I would ensure that if you're using piles for design, ensure a good initial pile load test to validate your design, if necessary, modify your design. Then the proof test we do on working piles. In a typical project, you may end up driving 50, 100, 200 piles. Even those you have to test them 1 in 50 or 1 in 100, depending on the code and depending on your belief in terms of workmanship, the ground conditions, etc. Because please remember, if you have a site, I know even for a building with the plan layout of something like 60 meters by 150 meters, the ground conditions are not uniform. If I look at from the northeast corner to the southwest corner, I find the ground conditions, the soil strata could be different. How do you ensure the same design will work for all of them? So what we do is in these 50, 100, 200 piles, we choose 1 or 2, 3 working piles and we test them for 1.5 times the design load. So that will again give you confidence that we are going to get a safe design, which is rational, also appropriate for our project, because you don't want any pile to fail. And please remember, piles are very expensive. I believe the cost is somewhere around 1,000 rupees, 10,000 rupees per meter. So when you're investing so much money in the foundation and the performance of the superstructure depends on the performance of the piles, you better invest some money on making sure the whole thing will work well. Then how do we load these piles in terms of compression? So what we have is what they call cartilage, which is nothing but dead load. You make sure all the load initially is placed and transferred away from the pile, and you can then take the reaction through a jack from the cartilage. Second alternative would be you can drive piles around and use them to take reaction. So this is another possibility. Sometimes we do it out of the existing ones in a big pile group, but for initial pile load test, I don't think it will be possible because we don't have too many piles around to take reaction from there. The third possibility would be you can drive anchors into the ground, which means you have to go fairly deep, maybe 10, 15, 20, 30 meters, so that anchor gives you the load from which you can take the reaction to. Out of these, the most common one are the cartilage and reaction piles. Occasionally, you do get them. Then in terms of the test, we do 2 types. Basically, what's called as a maintained load test, which means the load is kept for some time. There are 2 ways in which you can keep the load slow test, which means you wait for the deformations to become reasonably constant over a period of time, maybe half an hour, 45 minutes, 1 hour, etc., and then go to the next stage. Some of the people go, they say, no, we can't wait for it. So then they do a quick maintained load test. Then the load is kept only for a short period of 10, 15 minutes. And then the next load is applied. And the interpretation in each case is very different. And let me tell you, the deformations are more in case it's a slow maintained load test. Constant rate of penetration is where you push the pile with some kind of a mechanism at a rate of something like, say, few millimeters per minute. Again, this is not a very common thing, but some people have tried it. Basically, I would say most of our tests are slow maintained test loads, tests that we have. These are the kind of schematics for you have for the types of loading. The one on the left you can see is what you can have it settlement due to Kentley. I mean the dead load is due to Kentledge, the P, and the reaction is taken. The middle figure shows you the two anchor piles or reaction piles. You have a beam connecting it, and the jack is applied, is taking reaction from the beam, and that beam takes the load, transfers the load to the reaction. The one on the extreme right, you see the anchors which are deep below, and you need to have very strong anchor, which may go much below the pile itself, because otherwise you will not get enough anchor capacity. So these are the kind of things. Let me tell you, it's very, very expensive to do a static pile load test. It may run into a few 100,000, etc. This is one particular case where they had 2,000 tons of Kentledge setup, and you can see the blocks, cement concrete blocks, they had to pile them up so high so that you get the required one. Obviously, in this case, the pile capacity would be definitely 300 to 500 tons at least, so that they can get it. What we do in India is, of course, not always getting the concrete blocks. We sometimes use what you can call the sandbags, and you have to pile them up. And because they're all each hardly about 50 kilo in each bag, you had to use a large number. I know there are instances where we had gone for something like 1,000 to 1,500 sandbag, and that led to some kind of problem because the height of the loading increases. And if you increase the height of the loading, the chance of instability are very high too. And taking them up is not easy, so you have to do all kinds of things. And what you can see on the right-hand top corner is the jack which is placed. This is another interesting thing. I don't know whether I should say it or not, but in my experience, I found that, please don't pardon me in case I violate some kind of professional thing. Some contractors do preloading the previous night if you are not careful. So what you see on the day of testing is a reloaded pile. So don't leave the jack without attention. So I would like to warn you that this is a very important thing. So whenever we were doing the pile load test in IIT Kanpur, either we had our own watchman there to make sure there's no loading done in the night. I know one of my colleagues who left a company because he was asked to do this. He said, I won't do it. And they blamed him, saying that, your load tests are giving us very small allowable loads, whereas so-and-so is giving us much smaller one. The reason being the other person was loading it the previous night. Then we had to measure the displacement from jack, of course, gives the load. And when you want to measure the displacement, please note that the support system for the dial gauge has to be kept fairly far. Otherwise, the effect of the loading on the pile will cause displacements of the support for the dial gauges too. I'll show you some more pictures of this too. This is another schematic you can see, and you need, what you have is a very stiffened eye girder or set of them, on top of which we keep the Kentledges. And you can see on either side two pedestals on which the eye girder rests, and the jack you can see, and the reference beam from which we take the dial gauge readings. Don't take just one reading, you better have to have maybe two at least, so that in case the pile has a differential movement from, let's say, east to west or north south, you'll be able to find that out too. So one dial gauge, in my opinion, is not good enough. You need to have minimum two dial gauges. This is the pile load tests again. Basically, you can see very heavy sections you need in order to get this. A 600 mm dial pile, and dial gauge, the jack ramp is 350, and there are two dial gauges on either side. So again, the details, you can measure the load through either proving ring or one of those load cells, and you get the load from there, and the dial gauges give you the displacement. This is another schematic, and the jack is loaded by pumping. And I would recommend that this should be fairly far from the pile, because I'll show you another reason why the instability may lead to problems. So if you have a section where you can put the jack and pump a little far from the jack, it will be always good for you. This is what I wanted to say. if you want to have good measurement, please move the support system far away so the dial gauges are not affected. Fortunately, nowadays, you probably can use a total station rather than using a dial gauge to measure the displacements. And that would be one of the best ways to circumvent the problem of support settlements too. When you measure, obviously, these are the kind of things you expect. The curve on the right here is the total resistance. And then you have, I'm sorry, where is this one? We went back. The total resistance, but you would like to also know if it is possible to identify the response of the shaft and the base. And here I want you to realize, if you look at the base resistance here, it is mobilized at a very small displacement. Hardly, maybe something like 5 millimeters is enough for the full shaft resistance to be mobilized, whereas the base resistance need large displacement, maybe of the order of 10 to 20% of the diameter of the pile. I want you to keep this in mind because when I'm talking in terms of interpretation, this will be very, very useful. So, and the shaft resistance sometimes, because I said here, and you may end up getting, in case of sand, very dense sand, a reduction also because of the ultimate load, or what you can call the peak load may be more than the residual one. So you have to be careful with that when you are testing. And when you see a curve of this in a kink, you realize what's happening. So that's how I want you to look at the load displacement graph. So usually sometimes what we do is we end up not directly loading, we have what called cyclic loading. So let's say I apply the load first after about 200, 300 tons, unload it, go for the next cycle, which may be 500, 600 tons, then unload it, and then you go for the final cycle 3, where you find what is the kind of required ultimate load. In this particular case, cycle 3 has gone up to 800 tons. And you can see when you look at the displacements on the top time settlement, the whatever displacement occurs, it becomes constant under the first cycle. When you unload, we don't get back all the settlement that went in, the rebound is smaller. And you can see under the first cycle, the rebound is fairly significant, which is probably very little plastic deformation of 10%. But when you do for cycle 2 and cycle 3 under high loads, the rebounds are much smaller, which will tell you the behavior is going into more plastic state. The pile-soil interaction gives you into the elastoplastic range, and that will tell you how the ground is behaving. This is another thing you need to interpret when you are looking at the pile load test. So this is how it looks like. I want you to look at cycle 1, which has given you almost elastic rebound. I wouldn't say elastic, but hardly about, let's say, I think 1 millimeter was the permanent settlement. Under cycle 2, you can see the maximum displacement may be about 10 mm, but rebound is up to only 5, 6 mm. And in cycle 3, you have the maximum displacement of something like 23 mm, but the rebound is more than, it's 10 mm. So you can see the behavior of the pile is different under different load. This is how you can evaluate the elastoplastic nature of the same. We also like to find out, is it possible to measure the load in the pile so that what you do is, can I know how the load is getting transmitted to the bottom? This I'll come back later again in more detail, but in the refined testing where people like to know the load transfer, all you need to do is provide some strain gauges embedded in the pile itself, and from the strain gauge I can get the strain, from the strain I can get the stress, and from there the load. And you realize here, in all these cases, the shaft load is mobilized first, the base load is the last one to be mobilized. So you can say the top to bottom, it's a load flow. If you can think in terms of seepage, the load is the one that is getting transferred slowly to the bottom. And you have to see if is it possible to measure this kind of load transfer too. And you can also, of course, have a lot of instrumentation and find out, if possible, can I find out the toe displacement too? Let me tell you, it's a very simple device. All that you had to do is provide another telltale at the bottom. Some of the agencies I know, they're measuring not only the top displacement, but you can also measure the bottom displacement through another device, so that you know how much punching takes place into the of the toe into the base layers. This is another way in which you can get some more behavior understanding of the pile. I want you to now realize the interaction between the dead load transfer through cartilage. Suppose if I have the pedestals close to the pile and the cartilage is loaded as it is, you can see the surface footings through which the cartilage dead load before loading is transferring all the 500 tons, 600 tons to the soil, which means the soil below the foundation footings of the cartilage are soil is going down, it will try to subject the pile to down drag. I want you to understand because the implications of testing are important. If the spacing is large, this down drag will be less. But if the spacing between the two footings on the surface is small, this is what happens. So you can see the pile is initially, even before you load it, is subjected to down drag because the soil around the pile is trying to go down on either side. Now, during loading, what's happening is you're pushing the pile. So the pile is trying to go down and the load is being transferred to the pile. So the cartilage, the load on the footings is reduced. So the soil tries to move up and we need to analyze again in case of interference, what is happening to the pile. So whatever you think you're testing the pile may not be true. It's because of combination of down drag before the loading and reverse of that during loading of the pile. So please remember, you have to be very careful to keep these cartilage supports very far from the pile. The reaction piles are where we put in all around and then we take, you can see the piles in between these four stanchions you have, and from there you connect a girder and take it. We also have very similar problem with reaction piles too. So when I have these reaction piles, if they're too far, they're far, there's no problem. If they're close, we have problem. So this is a schematic basically. I have the two piles far away, at least 2 to 3 meters or minimum, at least 3 diameters away. That should be the minimum criterion. And then you install the piles on either side from which you can take reaction. See, when I take compression for the pile here, the other two piles will be subjected to tension or pull-out. That's why we call them reaction piles. So please note that the minimum distance is at least 2 meters or 3 diameters, preferably both too. And this is how you can say in terms of the load displacement response, very similar to cartilage 1, 2. You have a hydraulic jack which is taking reaction. We have a reference beam from which we measure displacements too. And this is what I would like you to again look at in terms of interaction. If the piles are too close, the zone of interaction with the anchor piles or reaction piles will affect the performance of the pile itself. So your test pile may be subjected to the effect of the adjacent piles. So whenever we do the group analysis, we have to do this. So one is in compression, the other two are in tension. So you have to analyze, assuming how much of load and displacements are affected by this. So this is the same thing as earlier. Before loading, no imposed load on the test shaft. But once you do the test reaction, please look at the soil movements. And the reaction piles will trying to move up, which means they try to pull the pile up. So the net movement you get will be due to compression under the load of the pile and possible upward drag force, which is from the surrounding shaft. So this is something you got to consider unless the reaction piles are very, very far. This is schematic. If I have sufficient distance between the test pile and the reaction pile, I don't expect any interaction or interference. But if you have close spacing, you can see the sort of the pull-out effect that you get on the test pile. the reaction pile is trying to move up, so the soil is trying to move it down, pull it down, and the Newton's third law tells you the test pile is subjected to soil which is trying to move up. So please remember, it's not that simple to do this. Now, there is another very interesting test which was developed recently. They were saying that why should I test the whole depth of the soft soil? If there is a bearing stratum at some stage, can I do a sort of plug test? So what they recommend is, instead of having a pile which will run into the soft stratum which hardly gives you any shaft resistance, so they put in a collar with a casing, and then they grout a plug in the bearing stratum. And this is done. So this I can call as a partial or short length pile, which is only in the bearing stratum. And I'm not interested in the response of the soft strata, which is not going to cause any load, which will not take any load. So please remember, this is another alternative you can have in case you want to concentrate only. This is valid particularly in our many coastal areas. The top 5-10 meters is extremely soft. Underlying strength of the soil is maybe 10 to 15 kPa, whereas most of the load I get is from the bearing stratum, which is probably 10, 12, 13 meters. It could be a stiff clay, a dense sand, or whatever combination you have. Then when we have this problem of measurement, the movement is not always immediately visible. There's always a certain slack, as you can see here. So what we do is we correct for the initial slack and redo the whole analysis. We modify the load displacement or unit size here, as you can see on the right side. Now, this is what I wanted to tell you. If you are not very careful with your arrangements, the whole thing may collapse. And that is why the jack and the person who is taking the reading should be very far. Let me tell you, we had 1 or 2 such accidents while I was at IIT Kanpur. So it's not something that it's a fictitious one. This is particularly true for Kentledge too. And in one particular case, I was there and my lab assistant managed to jump out of it. And because of the very high Kentledge, it becomes very unstable if it is not properly loaded. Okay, when you do pull-out test, is much easier because you connect the girder to the adjacent piles and the jack is pulling it out, so it's much easier to do the thing. So the reaction piles are under compression and the test pile is under pull-out. This is how it is. You can see the jack is above the girder and the 2 strips are going to the pile and attached there. So when the jack is pushing it up, the reaction pile goes up too. This is how you do the pull-out test. And measurement of displacement is about the same. You had to use these support systems far away from the test pile. Schematic for the one, the test pull-out response. Very similar to compression ones too. When you have lateral load test, we have a little more complexity. Most of the piles we have, when we test it, we don't have any pile cap. So what we are testing most of the time is a free head pile, which means the pile can, when you apply the lateral load, the pile head can displace and rotate. Now, this is a very strange thing. In all our testing, we think free head pile, but in practice, there's nothing like a free head pile. Most piles are embedded in a pile cap and pile rack, so which means the head of the pile is fixed. The response of the free head pile is different from fixed head pile. So in case you can want to improve it, you have to cast the pile in a huge concrete block to make it fixed head. So when you do the lateral test, be careful how to get the kind of thing. So lateral load testing is relatively easy in one respect, that I don't need a dead load. I can use the neighboring pile itself. I take a reaction from the adjacent pile and I put the load and take the reading. I think this will probably give us the, and then this is how we measure the displacement laterally, put the dial gauge, and the pile movement can easily be measured. This is how I would say it. You can also do a two-way test in the sense that I can get the response of both the piles simultaneously, or I can do a cyclic one. In terms of load unload, I can do very easily. So the testing for lateral load is much easier. Here you can see they're all free head piles. There's no pile cap. And when you interpret and design it, you have to convert the response from a free head pile to that of a fixed head pile. So often what we do is either use two piles, or if you have a pile cap, best is take the reaction from the pile cap itself. The fortunate part is that while the compression load can be the order of say 100, 200, 300 tons, the lateral capacity is smaller, maybe hardly 1/10 of that. So the reaction you need is very, very small, and we can use a pile group which is already existing. From there you take the reaction and get the load tested. And these are the kind of load test results. You can see the load has gone up to something like 12 to 13 tons, and the lateral displacement in this case is about 2.5 millimeters. And part of it is, only about half to 0.7 millimeters in the permanent settlement in this case, very small load. However, please remember, when you have lateral load, the problem of separation is a very serious one if your pile is going to be subjected to cyclic lateral loads. The pile will move, let's say, to the right, in which case there will be a gap between the soil and the pile on the left, and it can happen on both sides. Eventually, this separation may extend to a little deeper, so that when you're designing for lateral load, be sure how to interpret if you're going to have that cyclic loading. It could be due to wind, it could be seismic, it could be water load, whatever it is. I would say the best thing that happened in recent years, and fortunately for us in India, for the last maybe about 5-6 years, we have this Osterberg or O-cell test. What they do is, forget about your tent threads, anchor piles, etc. Take a jack, put it right at the bottom of the pile, cast it. Of course, it's a bit of cost. You are going to lose the jack. Once the pile is cast, you can't reuse it anymore. And we put it and cast the pile. And then this O-cell is now loaded. What happens is the bottom of the pile gets loaded in compression. The shaft gets pulled up. So simultaneously, you are testing both, and there's no need of any extra reaction to be built in. So we have this kind of thing. I believe in the Bandra Worli sea link is one of the earliest one, and now a lot of such Osterberg cell tests are being done by Afcons and L&T and several companies, which is the best way to test it under static condition. You don't need to spend so much money in building up the load anchor piles or anchors or reaction piles, etc. Invest that leaves amount of money on O-cell, put it down at the bottom of the pile, jack it up. So the soil at the bottom is under compression, and the shaft above the jack is under load. Now the O-cell can be at the bottom. This is how it is, the one that you can see the detail. And we, of course, you need to have a pipe to jack it up and measure the displacement, etc. These are all, they come with the usual setup too. Some of the Osterberg cells are also embedded at the center. The advantage with this is that you get some compression and shaft resistance below and shaft resistance above. So, but the only problem is the amount of shaft resistance you get on the pile above the length is limited, so you may not be able to load it as much as you want. For very deep, long piles, this is okay. So this is the schematic. Before loading, absolutely very stable condition, no imposed load on the shaft or the base. And during loading, again, no external loading. And what you can see, the shaft above the jack is subjected to upward force, and the pile below the jack is subjected to a downward force. So basically, you can find the variation of the load. And here again, I would like you to look the standard test with cartilage. The load is applied at the top, so the load flows from the top to the bottom. The maximum load is at the top and the minimum is at the tip. Whereas in the case of Osterberg cell, it's exactly the opposite. The maximum load is at the tip and the minimum load is at the top. But in terms of the interference, etc., zone of influence, there is none. So it's much easier to analyze O-cell test, as you can see here. And in case you have somewhere in between two, you can modify your analysis where you want the shear to be mobilized, depending on how you do that. So these are one of the most powerful possible tests that we have. And for the instrumentation, you can see apart from the reinforcement cage, you need the displacement transducers. Everything is electronic, and of course the hydraulic jack. Hydraulic supply line will add the fluid pressure to the jack. This is single level, and you can measure the displacement at the top as well as at the O cell, and you have the pressure measured there too. And this is how the load displacement looks like. You can see the blue line is the response of the pile to compression. The red curve is the displacement, the response of the pile to upward force. So you get complete behavior from the instrumentation plot, and you know what's happening to the pile much more in detail, much neater, quicker, and then you can do the whole thing. This is how I look at the diagram, and I can immediately find out the upward top moment of the cell is probably about 10 millimeters, and I could get a load of 27. So I know the shaft load. So if I look at the downward one, I know the length and then the total load, and very similar behavior you got. But in terms of displacement, the bottom part is much more than what it is in the upward one. We can also use some strain gauges and get the load displacement response at each level. I'll come back to this a little later in terms of analysis. This, of course, is very expensive, but if you want to study the behavior and find out what exactly is happening in terms of load, and you can see the way load is being transferred at each stage of loading, how much is going to shaft and how much is going to the base. This will be a better picture. Now, I think probably Dr. Ravikiran Vaidya will talk about the dynamic methods. I just want to just pass on through them. We do what's called as a simple integrity test. We want to know whether the pile is solid, complete, proper or not. It's a low strain one, and from there I can get the type of pile, any defects, etc. From the simple response picture that you get, all that you do is you tap it, measure the response in terms of a accelerometer. And if there is a defect, immediately it will come out. And Dr. Vaidya would be the best person to talk about it because he has been doing it. The idea is you can find out if there's a bulge, if there's a necking, if there's a crack, or if there's a poor concrete. You have soil stiffness varying method for the casing problem is there. What kind of soil is at the toe, etc. These are the kind of things you can do that. Basically, this is a schematic of the defects that you expect, and you can find out. I would recommend that if you have a large, good project, please go through integrity testing because the concreting is not always perfect. The people at the site may not always be as efficient or as expected that they'll be perfect. So it's always good to find out what possible defect is there, and this pile integrity testing is much less expensive. You can do that. I'm aware of 2 or 3 problems layer. If I have a soft clay layer somewhere, suddenly the bulging takes place, as you can see on the left, and then you may not have concrete in the bulge too. And there are any number of cases where, in case of board cast in situ pile, the bottom is not properly concreted. So these are the defects that you can easily find. The other one will be dynamic pile testing, which is the pile driving analysis. You can find out the capacity without doing a static load test. Come back to our concept again. As I said, please note that a friction aspect of it, or shaft resistance, needs a very small displacement, and you get full mobilization of the shaft resistance. Whereas for bearing, you need large displacement. We talk in terms of 10% of the pile diameter. So if I have a 600 mm pile, imagine you had to go for 60 millimeters, which is very, very difficult. So we rarely manage to get the full mobilization and bearing. Most of the time, we end up getting only the shaft resistance fully mobilized. in this case, I want you to tell me whether it's all fully shaft or is there some possibility of some end bearing too. As I can see, the total displacement is around 10 to 15 mm. So I would expect most of the shaft load is mobilized in this case, and some end bearing has taken place. And if I look at the curve, it's not still reaching the ultimate value. It's still not horizontal. I mean, the load displacement curve doesn't drop down. That's how I look at it too. And there are different ways in which you can interpret that. I may not go in detail, but I would like to say there are several in the literature which say, if you haven't gone to failure, how do I get the ultimate value? One of the parabolic methods is you take different intercept, increase the, I mean, at regular, say 5, 7, 10, 15, 12.5, 15 mm displacement, and look at the increment in load, and you will realize that asymptotically it will die down, and if you extrapolate the load increments, it will come down. This is one of the earliest methods. People have been using like plate load test. You plot the settlement versus load on a log plot where the kink occurs, but honestly, this is not the ultimate load, and I would say all you get is a change in rate of displacement mobilization with the load. So I'm not very confident or useful for this method. Okay, this one of the good method which has been given by Shin from Malaysia back in 70s is that load displacement curve looks like a hyperbola. As you can see here, hyperbola is where you have gradual increase and finally it asymptotically reaches the ultimate value. So he fits in a hyperbola, and what we do is we plot settlement divided by load versus settlement, and it turns out to be a straight line. The slope of the straight line gives me the inverse of the ultimate load, and the intercept at the top here, basically if it's a linear one, I can usually calculate the initial slope of the load displacement or initial pile soil stiffness. So I can get these two from the hyperbolic or Shin's method, which is very, very common. And if you look at it, you can see here, if you are able to separate out shaft and base load, I can plot these two separately. This is side friction, and you can see the slope is far higher, so which means the inverse of it is less, and the end bearing is much higher, so the slope is smaller. So you can easily separate out these two in case you're able to measure, and then use appropriate factors of safety for the design. So these are some of the methods that I could find out in the literature, how to analyze the load displacement graph and try to get your working load. This is quick maintain load test. Davison suggests that you look at the drawdown curve, obtain the load corresponding to delta is the elastic compression of the pile plus 0.15 inches plus d by 120. This is the American one. Shin's method, I told you, the hyperbola, and you can use it for both quick and slow maintain load test. The Belgians, they have a slightly different one. They put on two lines. This is the double tangent method. And similar to that one people have. The Brinch-Hansen recommends that you find out the constants C1 and C2 and then use them to get your ultimate value. Similar ones you can adopt whatever you think is appropriate. So, I mean, again, some of them to be illustrated through figures. This is how we look at it. Failure criteria. Can I go to the ultimate value or should I stop at 10% diameter of the load? So maybe, whatever is the maximum displacement. And you can see a kink here, which will tell me the yield load. So once I get the yield load, the rate of displacement is very high. So that's how I look at it. This is the tangent one. You have initial tangent and the tangent from the later part to get that. Davison offset method. Elastic compression plus d by 120 plus 0.15. He said this is your failure load. That's how we assume and then get the values. Shin's hyperbola. You can look at the actual curve here, which is looks like a hyperbola, and we convert that into displacement by load versus the displacement. I fit a straight line, the slope is inverse of the ultimate load, and C2 gives me the inverse of the initial slope. So I can get both this information. You don't need to go to failure because hyperbola is one which has asymptotically reaching the ultimate value. And this straight line gives me the ultimate load without any problem. So bring chances is here. We takes in terms of different percentages of load, extrapolates it, say 50%, and then go to 1.5 times that, and you can get that. This is how I like to interpret whenever I have a load, then I can see there's a very sharp drop. Immediately I realize it's a friction pile. Whereas this is typical friction and end bearing pile because you can see the displacement now is going up to 14, 15, 16 millimeters, and we still are not reaching the ultimate load. So then I know it's both the piles. So when you want to interpret, please look at the load displacement graph and just don't look for only the ultimate load or the safe load, whatever it is. You try to get how is the pile responding to you. So here is a strain softening on the right side. The peak load is obtained, then the load drops down. So which means that when you take a factor of safety of at least 1.5, you're sure the shaft load will still be available. And you can see if you have a gap also, initially some friction load is mobilized, then again the pile catches, which means in this case, for all you know, at the tip, there's a soft pocket, and the pile after moving down is able to meet the hard one too. And if the concrete is weak, this is what happens. I would have expected the curve on the right, but because the concrete is sheared completely, I get a very small load. Again, similar to one, what kind of failure you can get. And sometimes you get the, if you have a hard drop, then the pile gets sort of bounced back because of the hand bearing kind of thing. When you're interpreting, you have this problem, as I said, the down drag effect due to cartilage, the groundwater conditions can change. So when you're testing, you know what is the groundwater level. Suppose the groundwater level changes, the design has to be accordingly corrected. When you are doing bridge foundations, you do a pile load test, but you have to allow for scour. So please remember, these are possible interpretations too. So when you have scour and you expect, I don't want the capacity to be measured during scour, you put in a casing so that the pile goes below the scour depth. And the same thing is true for down drag too. You don't want the, if a soft clay is there and is going to cause down drag, I want only the load carried by the soil below the soft clay, then you put a collar and do the test. Pull-out test is relatively easy because all that you do is you apply and measure the displacement, and here you get a very sharp change in curvature because it's a shaft resistance alone, and so allowable load is simply the ultimate Q load by factor of safety of 2.5 whatever it is. This is a typical pull-out test, and I want you to note that displacements here are hardly about 2 millimeters, less than that. There are 2 piles tested at a particular site, and the pull-out load is hardly, it's good, 70 metric tons. Load transfer, as I said, how it flows. Initially, when you apply small load, very little load goes to the base or even bottom of the pile. When you increase the load gets transferred deeper and deeper. And finally, at the maximum load, some amount may go to the base. So this is how the flow of actual load takes place. Many times we assume as if all the load goes to the base, but it's not true. At working conditions, very little goes if the soil at the top is reasonably stiff. So how do I take care of it? Is it possible that we can measure at different depths? So there's a very simple way. You provide a couple of steel bars within the cage to which attach your strain gauges. And these are all embedded. Of course, strain gauges are properly wrapped. And then you instrument the whole pile within the cage and you can take the readings. You can also put a load cell at the base in case you wish to do that. And you get the response from the bottom too. As you can see, this is a load cell at the base. So very interestingly, I got one particular case study where they had done several strain gauges kept at different depths with a load cell at the bottom, and we could get the response of the pile at different depths. As you increase the load, you are able to find out how the load is flowing to the bottom. And this was very powerful and useful because once we had this data, we could even find out the shaft resistance mobilization as a function of displacement. So this is one of the best cases where I have seen very short piles, 3 to 5 meters long, and where they have done the measurement at the base and along at various depths. So imagine the kind of fortune you have if you can do this kind of testing, a little more expensive, but then you have very useful data. So for those piles which we have, you can see how much is load transferred between say 0 to 1, 1 to 2 meters, etc. How much is going to the base. So these are the kind of interpretation one can do from there. And this is how we are able to plot the mobilization of shaft resistance with displacement, mobilization of base resistance with displacement, and of course the total load with displacement too. And I want you to notice that in all these cases, the base load is mobilized after some finite displacement at the top. So don't expect the base load to be mobilized right from zero displacement at the top. This is one of the very useful test data we got somewhere. And so these are the summary of all the tests there, 600 mm, 400 mm diapiles, piles, different lengths, etc. And this is another pull-out test we had, where you can see how the displacement is taking place too. And the rebound tells me what will be the net plastic deformation, because the pile, once you remove the load, the elastic rebound of the pile is more, and the net plastic settlement is due to that of the soil. So we can work out what is the two components in terms of the rebound gives me the out of the total displacement, what is the net displacement due to the soil. So this is another example of lateral load test. In this case, you have very good rebound in this case too. Now you can see the cyclic loading. First load is only up to something like 15 tons, and the rebound gives me 1 mm of net settlement. And then the second rebound goes up to something like, let's say, 34, 35 tons, and the rebound is around 3 millimeters too. And you can see what's happening under each cycle of loading. So that's how we can find out this. For different lengths, we have the data, actual load test, lateral load test, and you get very useful data from there. Now, this is another typical case we got. You can see the test pile. Immediately, I realized the way the load settlement drops down after 5 millimeters. You can say there hardly any base load at all. Even though it's an 18 meter long pile, the base resistance is negligible. So which means there is a gap at the bottom, or the concreting hasn't been done very well too. This is a better one in terms of load displacement. You do get a typical hyperbolic response. So possibly both shaft and base loads are being mobilized in this case. And you can see if I look at 5 mm displacement, the load is around 150, 170 tons, whereas the rest of it is probably because of pile load test. This is compression test, 400 mm, 18 meters. So base again, initially it looks very linear, but once you go to the second load, you get much larger one. And most of the time people try to stop at 12 mm to 15 mm displacement for the convenience in terms of load. They may not be able to generate too much load. So in this case, it's about 200 tons. Here it's 250, very similar draft too. These are some of the load tests that were done in some places in India. Now here is another very strange case. You have a shaft resistance and everything is plastic. You can see the rebound is hardly some 3 to 4 millimeters, which means it's very high plastic deformation, which I would be very careful why it's happening, and we'll have to go for a bigger display. Now the problem here is that They should have stopped somewhere here, but they allowed the pile to sink from once it reached the maximum load, they have allowed it to go punch through the soft clay. And that is the reason because of the reason why the rebound is very, very small. The pile is allowed to fail too much, which shouldn't have been done. So these are some more compression test piles. We try to analyze them. This is almost linear in this case, but you can see a kink here at about 180 tons, and then it picks up and then goes here. And it hasn't reached the failure. So we like to analyze and get back whatever the data are. Small load cycle here and large displacement. Now what we try to do in these cases is that one of my students has come out with a simple model. We say that the shaft and the base I can represent by means of simple Winkler type nonlinear Winkler one. So if I look at the total pile, this is the hyperbolic response. Initial load displacement, the slope is Kp, coefficient of the pile soil displacement, and the P ultimate is the maximum load. Whereas in the case of shaft load, the initial slope is defined, the spring constant, if you want to call, or modulus of shear stiffness is K tau, and the shaft resistance is tau max. And for the base, I put it as Kb, and let me move this, Kb, and this is the ultimate base load. So we made simple assumptions with regard to the mobilization of shaft and the base load through Winkler springs, and then we combine them to get the overall response. And we write the simple equation. If I look at the pile, this is shaft resistance, tau into pi dl is shaft area, base load into base area, that gives me the ultimate load. At any displacement, this is the value. So I'll try to fit in the hyperbolic relation, and I measure at two displacements, the loads and the displacement, P1 and P2, I can get in terms of the analysis. And what we found very interestingly was, this is the average N value along the shaft, N value at the pile tip, and we had estimated basically this average for the shaft, and this is the average N at the base, and of course we do correct for the N if it is at depth, and these are the loads we have been able to estimate. Now look at the maximum shaft load. Unit shaft load is 34 kPa, ultimate base load is 16.9. What we then found out was, can I correlate them with respect to the IS codes? And when I do that, I could verify that our codes are not, matching with this. When I estimate the shaft load, I get 34 kPa, but according to the code, I get 88. Conversely, when I look at the base load, it's not too bad in this particular case. In the second case, this is another place in, I think, Assam, West Bengal. I get shaft resistance from my analysis 115. The code gives me 58. And the base resistance 12.8, as I'm getting 8.2. Similar to that, another place, 56, 98. Can you see that the code gives me very high value, but I'm not able to get it? And in the third case and fourth case, it's not too bad. So now I realize that if I just go by code, I may not be able to get the best of the lot. So what we have been trying to do now is not just estimate the ultimate load alone, but you can analyze the pile to identify the defects. You can get the initial stiffness. You can diagnose the defects if there are any, and you can also get the load transfer. So what I want to share with you is that pile load test is not simply for getting allowable load, but you need to use it to get much more information than is possible. So I just would like to end up my presentation with a nice picture using rocks, but you can test it this way. And I always end up my presentations with my signature. People think geotechnical engineering is a science, but when you practice it, it's an art. In the sense that no equations will give you the answer. You need to have more insight into it, more like an artist, more like a Zagi, more like in terms of a clairvoyant who knows what's happening inside the ground. And this is what I wanted to present, but I'll be very happy to share with you if you have any queries or discussion that you would like to me to answer. Professor Reddy? Yeah.
Sir.
Yeah. I would like to interact with the participants if they have any queries. So,
There are hand raises, sir, from the participants. I think participants can unmute and interact with sir.
so
I request the participants to raise their queries. Or you may post your query in the chat box also. I can pose on your behalf.
I hope that the presentation is clear enough
Sir.
that you can apply most of it. And at any stage you want some clarification, please feel free to contact us too. We'll be able to share with you whatever we have.
Thank you very much, sir, for your detailed presentation on file load test. So generally, people will study how to arrive at safe load capacity calculation from load test data and all. So you have clearly explained based on the load settlement pattern what extra information we can gather from response of ground into the applied loading, how shaft resistance is mobilized, how end bearing resistance is mobilized. So thank you very much, sir.
So that's why I'm glad, you have summarized very well. It's not so much simply getting allowable load. One more thing I would like to add, I should have said earlier, the contractors like to get away with only loading in 4 steps, 25% of the estimated ultimate load, 50%, 75 and 100%. Please try to increase the number of increment, 10%, 20%, like that. If you go, you get a much better response and then which you can interpret easily. This is always a desirable thing too.
Not only that, for each load increment, they are not waiting as per the specifications given by the codes. They are doing in a hurried manner and they are not getting the exact settlement under the load.
That is the problem, the contractors are interested only in money and getting away with it. They're not interested in trying to ascertain properly. So the site engineer and the geotechnical engineer has to ensure that you get proper data from the load test. It's very valuable. As I said, it costs few lakhs. Each pile load test 1 to 2, 3 lakhs. Why are we not using that so much of investment and get as much information as possible? And please be careful that they don't preload the previous evening. Then you end up getting only the rebound effect and reloading effect and not the original one. And they get away with it. So please, I have nothing against the consultant. The contractors are practitioners, but we have to be careful that we do justice to the project for which we are all responsible. Thank you, Professor Reddy.
Thank you very much, sir. So participants, any questions? If there are no questions, we'll close the session once you fill up your attendance sheet. So those who have joined late, not only related to this topic, you are free to ask any question related to the title of the FDP, both shallow or deep foundations. With vast experience, whatever Professor Mazo has got, right, he'll be able to answer your query, right, effectively. So if you have any question, practicing engineers are there, your field issues, anything are there, you can discuss.
Yeah, please share them. Where?
Prasad, I think Mr. Prasad has raised his hand. You introduce yourself and raise the query, sir. Maybe your audio is muted. First you unmute your audio and then raise your query.
Looks like no.
So even if you have queries which you are unable to raise now, SAR will be available on Monday morning also. SAR will be delivering another lecture on lateral load piles. Right. So during that time also, you are free to discuss any query which you have related to both shallow and deep foundations.
Okay then. Huh? Have a nice evening. Thank you, Professor Reddy.
Thank you very much. Sir, here is one question from Lokesh.
Yeah.
How to test a pile when surrounding ground is soft?
That's going to be a very difficult one in the sense that you can't use the cartilage. Then you have to go for reaction piles in this case. If the soft ground is there, as I said, you will have a lot of down drag. So that is where you had to go for cartilage, reaction piles or anchor piles. You cannot do simple cartilage load.
So Lokesh, I hope you got your answer. Any more queries? Okay, sir.
Okay then. Huh? Have a nice evening.
Thank you, sir. So I request all the participants to fill the attendance sheet and also go through the presentations available on YouTube, because as per the guidelines of AACTE, at the end, right, on the last day of the program, we need to have a test, right? So during your leisure time, try to go through the lectures, right? YouTube links are already provided to you. So using those links, whatever portion you have missed, right, try to listen. So thank you all for attending this evening session, and look forward for your right active participation in the next week, right? So I congratulate all of you for successfully completing, right, first week of this faculty development program, right, attending this and simultaneously attending to your regular work at your institution or organization, right? So I appreciate your interest, right, in spite of having other engagements, right? You have shown interest in updating your knowledge, right? I hope all of you are enjoying the sessions and definitely gaining some extra knowledge, right, in the area of shallow and deep foundations, right? So feel free to raise any query either to the speaker or to me, right? Okay, then I thank you once again. Have a happy weekend, and let us meet again on Monday at 8:30, right, for the lecture by Professor Madhav on lateral load piles.